All right, welcome to part 2, and I have my fingers crossed hoping that this function fits on this graph. So first thing we want to do, factor this denominator. So we have x minus 2, x plus 2, some more difference of perfect squares, and look for any removable discontinuities. So we can factor out that x minus 2. So we have a removable discontinuity at x is equal to 2. The function's going to behave just like x plus 3 times x minus 1 divided by x plus 2. So we want to substitute that 2 back into that equation to give us our y coordinate for this. So we have, 2 plus 3 is 5, 2 minus 1 is 1, divided by 2 plus 2. So we have this point to 5/4 where there is going to be a hole in the graph. So 2. And then 5/4, so it's 1, and 1/4, so it's going to be about there. Essential discontinuities, we set our denominator equal to 0, so we have it at x is equal to -2. We set our numerator equal to 0 to find our zeros. So that will be at -3, 0, and 1, 0. So -3, 0, then 1, 0. Now, we want to look at this and see that we have an oblique asymptote, because if we multiply out our numerator, we get x squared plus 2x minus 3. And since the exponent's greater than the numerator, we have an oblique asymptote. So what we need to do is do some long division. All right, so x squared divided by x is x. We take that x, multiply it by our entire numerator, subtract, and oh look, we have 0. So our oblique asymptote is just at y equals x. Fits on the graph. So now we want our y-intercept, so we substitute 0 in for x, so that's like that will all be 0. So we have -3/2 is our y-intercept. So that's going to be right here. All right, so that gives us a pretty good idea of what's going on over in this section. So it's going to be close to the asymptote, intersect the, let's draw it so it actually intersects. So all right, it's third time's the charm, I guess. So it's going to be close to this asymptote, intersect this removable discontinuity, intersect this x-intercept, intersect this y-intercept, and then get close to the asymptote. Pretend it's a smooth curve. Now, over here, it's going to do something similar. It's going to be close to the asymptote, close to the asymptote, intersect that 0, and then go close to the asymptote. If you wanted to figure out a little more exactly, then you could substitute some other points in, like -4 or -3.5, -2.5, whatever. Some other graphing that some people had some more questions with is some piecewise graphing. So remember, 4 to the x plus 2 is an exponential function, so it's going to look something like this, except shifted up 2. So when x is less than 0, so we want to substitute in those changeover points. So we substitute 0 in. 4 to the 0 is 1. 1 plus 2 is 3, so we're going to have an open circle at 0, 3, because x is less than 0. Now, the way that we end up graphing our exponential functions, we want to find that y-intercept, and then they're always going to have a horizontal asymptote at y equals 0. But that plus 2 is going to shift it up, so our asymptote is going to be at y equals 2 instead. So as x approaches -infinity, 4 to the x plus 2 is going to approach that asymptote of 2. Now, between 0 and 4, we have x minus 2 squared, so we substitute 0 in, and we end up with 0 minus 2 is negative 2. Squared is 4. So we have a closed circle at negative 2, 4. This is going to be a parabola with a 0 at 2 because the minus 2 is in the argument, so it's going to be shifted to the right 2. Now we can substitute 4 in. 4 minus 2 is 2. 2 squared is 4. So we have an open circle at this point for 4. I don't know why my drawing tonight has not been ideal. So this is a parabola. There we go. So it's a parabola looking like that. And then negative absolute value of x. Remember, absolute value of x is our v, but the negative multiplied in the front is going to cause it to be a concave down v. So we substitute 4 in. So we have this point 4, negative 4 that is going to be filled in, and then is going to have a slope of negative 1. So it's going to look like this. Now moving over to this one. So when x is less than or equal to negative 2, y is equal to 4. So this is just, we find negative 2, and then it's just a horizontal line. Now, x plus 1 cubed, so our cubic function, remember, looks like this, but that plus 1 is going to shift it to the left 1, so we're going to have a 0 at negative 1, or when x is equal to negative 1, and then if we substitute negative 2 in, so we get the point negative 1, because negative 2 plus 1 is negative 1, negative 1 cubed is negative 1. So it's going to curve like this. We can substitute 0 in and get 1. So we're going to have a function that goes like this. 1, we have 2 cubed is 8. So it's going to increase like this. So it's that cubic graph just shifted over to the left, and we're only looking at it from x is equal to negative 2 towards infinity. All right, so negative x plus 1 is our function. So negative x plus 1 is just a line. Slope of negative 1, y-intercept of 1. So we're looking at this when x is less than negative 3. So we substitute negative 3 in. So we get the point negative 3, 4. And then our slope of negative 1, so if we substituted negative 4 in, we'd end up with 5. Negative 5, we'd get 6. So that is what our line is going to look like. Absolute value of x minus 1, we've got our absolute value v, but the minus 1 is going to shift it to the right 1. So we substitute negative 3 in. Well, sorry, first, we've got our 0 at 1 because it's shifted to the right 1. Substitute negative 3 in, so we get negative 3 minus 1, it's negative 4. Absolute value of that is going to be a positive 4. So in this case, we're just going to fill that open circle in, because then it's going to intersect there. Then we substitute 1 in. 1 minus 1 is 0. Oh, look, that's that whole piece. So our negative x plus 2 is another line where our slope is negative 1, y-intercept is 2, so when x is greater than 1. So substitute 1 in, so negative 1 plus 2 is 1. So we have an open circle at the point 1, 1. Here I can get a little more precise with this, although then you see how not great my lines look. So we have an open circle there. It has a slope of negative 1, so we intersect this point 2, 0. 3, negative 1, 4, negative 2, and you get the picture with this. All right. Now, let's take a look at this last one here. So we've got x plus 3 squared. That's going to be a parabola shifted to the left 3. So we know we have a 0 at negative 3. We substitute negative 2 in, we'll get the point 1. We substitute negative 4 in, we also get 1. When in doubt, you can always just substitute values in, and whatever your x value is, whether it falls on one of these three intervals, that's the function, the piece of the function that you're going to substitute it into. So we have a parabola that looks like this. 4 minus x squared. So it might help you of looking at it like this. It's negative x squared plus 4. So that is another parabola, but it's moved up 4 and then reflected over that line y equals 4. So we substitute negative 2 in, and we get 0. Because negative 2 squared is 4. 4 minus 4, 0. We substitute 0 in. We know we have that y-intercept at 4, and it's going to curve down parabola-like in here. It is a parabola, just my drawing is, you get the idea. And then at 3, well, if we substitute 3 in, we end up with negative 5, and there'll be a closed circle there. We have another 0 at 2, and it's just looking at following the pattern that we see with the different translations on functions and what parabolas are supposed to look like. So then x minus 3 squared, you guessed it, another parabola, but shifted over 3. So when x is greater than 3, we substitute 3 in there, we get 0. We substitute 4 in, we get 1. 5, we get 4. And then 6, we get 9. So it's off here. So we get yet another piece of a parabola. Thanks for watching, and happy studying.